Welcome you all to this course on defects in materials. In the last class, we looked at the different types of defects in FCC lattice. That is especially dislocations in FCC lattice, we try to look at it. What are the types of dislocations which are possible in FCC lattice? And that what we considered was when the striking fault energy of the material is high. That is the various types of possible dislocations which it can form. Okay. When this and what is the type of interaction which can take place between these dislocations. Okay. Today, what we will try to do is that look at cases where this cases in materials where the striking fault energy is low. Okay. As such, if we consider dislocation in a lattice, okay, the tendency essentially is that if a dislocation of the type A by 2, 110, which is a perfect translation vector in the FCC lattice, if it tries to split into a dislocation, for example, consider a hypothetical case. Then we will find that here it will be, the energy will be A squared by 2. In this case, it will be 2, correct? By 16, correct? This is plus A squared 2 by 16. So the energy here is greater, so this reaction is possible. What it means is that all perfect dislocations would like to reduce their energy, okay, by splitting into partials which have got Burgers vector which is smaller than that of it. This is an type of reaction, okay, which because of reduction of self energy, dislocations will always try to go through this process, okay, to reduce their energy. So this is one inherent property of the will dislocation split into partials and create striking fault or not? That is the question which have to be considered. And another is that will in all material a striking fault will form or not? Okay. Let us try to look at that case. Okay. Here what we are considering it is an FCC lattice. Okay. I will just (1, 0, 0). Okay. These are all the positions which atoms are going to occupy in the lattice, correct? Let us look at the case of 100 plane or 001 plane. 001 plane means that essentially atoms which are arranged in this XY plane which we have to look at it. That is what is shown here. Okay. These are all the two directions, 110 direction and 1 bar 10 direction, because there are two close packed directions which are going to be there. That is at every plane here. This will be one close packed direction, this is another close packed direction, correct? That is essentially what is being shown here. What is the striking sequence here in this direction? If we look at it, it is going to be an AB type of a striking sequence. Suppose we consider this plane, okay, this is the B plane, this is again an identical A plane comes, AB type of a stacking sequence. Okay. Here we assume that the atom on the B plane is sitting at this position, which is going to be the low energy. Okay. This atom, by a moment of a perfect dislocation, will shift from here to this position or from here to this position. So that means that the movement of the atom goes from a B position to another B position. Correct? That is what essentially happens in this system. So there is no other choice which is available. The other choice which is there is that this atom can be moved from here to this position, which will be essentially a partial of the type A by 2 0 or 1 0 0, because we can consider this reaction right. This reaction we can consider. If we look energy wise, this will be A squared by 2. Here it will be A squared by 4. Here it is A squared by 4. So there is net gain or loss of energy is going to be there. Okay. But added to that, the atom has to be moved from this position to a position which is identical to an A position. That is the only possibility. And this vector essentially is like a partial translation vector, because this is not a translation vector in the FCC lattice. Correct? That sort of a reaction in principle can happen, but that moves atom from here to a position on top, which is essentially looks like a high energy position. Okay, some energy is required to move it here, some energy is to from this position to come back to this position. So essentially this sort of a dislocation reaction, okay, there is not much of gain in energy. Okay, this need not happen. Let us take the case of a 110 plane. The same is true in this case also. In this case also the close back direction is 110, A by 2 110 is the bias vector of the dislocation, close back direction is 110. Okay. And here also the stacking sequence is AB, AB, AB. Okay. So that means that A layer and the B layer below this A layer is being shown here. Okay. So atom shifts from one A position, B position, okay, by a translation vector of the perfect lattice, it moves to another translation vector. Nothing else, there is no other possibility where it can go. If we think of a partial which can move it, like we considered in this case, that partial moves it to a position which is a high energy position, because it is almost like climbing up the hill. Correct? What is interesting is the 111 plane. Okay. In 111 plane, here if we look at it, essentially it is a hexagonal type of a stacking sequence. Okay. In this, the stacking sequence itself is ABC, ABC type. Okay. Let us look at it in detail. Here what I had shown essentially is the various close pack directions are shown in this. Okay. Let us look at the arrangement of atoms in this plane, okay, which is shown in this particular slide. Here this is an A layer which is being shown, and this is an atom on the next layer which is a B layer. Okay. And there is another position. This position is essentially a C position, because which is what is being A and B and C position. What is interesting about this arrangement, that is whether the atom occupies, the atom on the next layer occupies B position or C position, essentially it is in the same energy state. Okay. by moving over from B to C, it is reaching a stage, okay, which is the same as that which was before. That is because there are two possibilities for the position, that B position. There is a possibility that it can go from B to A, which is a high energy position, or another alternative from B, not to B but to a position which is C. That possibility is also there. If it moves from the position B to another B position, that movement can be brought about by a perfect translation vector. Okay. Whereas if we go from here to here, okay, the translation vector is not a perfect translation vector in the FCC lattice. That is essentially what is being shown here. Okay. This is an atom which is occupying this B layer. By a movement of a vector, these vectors, if you look at it, this vector will correspond to essentially a 1 bar 1 bar 2. Okay. Similarly, we can find out the translation vectors in this direction is A by 6, it will be 1 2 bar 1, and in this direction if you look at it, it will be A by 6 2 bar 1 1. Okay. By a movement of a partial which moves atoms from atom which is sitting at B position to this position, whatever be the partial, it does not matter which partial we use it, it moves from B to a C position. The stacking sequence essentially changes from B to a C position. It does not matter which partial is responsible for it. Correct? That is one thing which one should understand. Okay. That means that the stacking sequence is altered in a particular way by atom going from B to C, but that can be implemented by a movement of the choice of three partials are there to implement it. Okay. Here what I had shown is perfect translation vectors which will move this atom from B layer to another B layer or to another B layer, or it moves to another B layer. Right? The choice, if you look here, now essentially is that any of these perfect translation vectors maintains that order. Correct? ABC stacking sequence is not changed. The stacking sequence remains the same. Okay. The same thing I had just shown in terms of a stacking sequence itself. Here we have considered with respect to an atom position, okay, that is A layer, and how a movement of an atom from B layer by what is the type of partial which will move it from B position to a C position, that is what we have considered. Okay. So in a perfect FCC lattice, the stacking sequence is ABC, ABC, ABC type, which all of you know. Okay. In this, suppose I introduce a fault here by a movement of a partial. The partial which we consider, that which I mentioned, that is like this. Or A by 6, 1 2 bar 1. Any one of these partial, okay, moves an atom from B position to the C position, correct? So then the stacking sequence, when this partial moves, it not only moves the atom in that layer, all the atoms in that layer above that plane will all be shifted by the same translation vector. So B will be shifted to C, that is what is being shown. C will be shifted to A will be shifted to B will be shifted to C. Now if you look at the stacking sequence which has come because of the movement of a partial, it has become ABC, ABC, okay, AB, then ABC, ABC on either side. Okay. So here if you look at it in this region, which is a CA, CA type of a stacking sequence is there. That is, it's nothing but an AB, AB type of a stacking sequence. That is what it occurs for a hexagonal lattice. Okay. When such a type of a stacking sequence occurs in a hexagonal lattice, we call that as an HCP structure, hexagonal closed packed structure. So essentially, the stacking fault which forms has got a unit cell of HCP there. Before coming to that, let us look at what is the other way in which the same stacking sequence can be generated. Okay. In this, suppose I remove a B layer. That is, this is the ABC perfect stacking sequence. I remove B layer, then what will happen? When a B layer has been removed, then the stacking sequence now becomes ABC, A, B goes CA. So essentially the same stacking sequence comes. So either by movement of a partial which moves an atom from one position to another position, or removing that layer itself, both are equivalent. Right? Both generate the same type of a fault in the stacking sequence. That is what is being depicted here, okay, where part of the A layer has been removed. When the part of the A layer has been removed, then this has become ABC, BCA. Okay. So this stacking fault we call as the Frank fault. Okay. So Frank fault also, the stacking sequence remains the same, but the mechanism by which the fault has been generated in these two cases are different. Okay. It does not matter, but what is important is, as far as the fault is concerned, this type of faults are called as intrinsic stacking fault, where either one layer is just moved from one position to another, or a layer has been removed in the stacking sequence along one direction. They give rise to an intrinsic stacking fault. What will be the difference which we will observe is the type of dislocation which is responsible for it. In one case, the stacking fault will be attached to a dislocation which has a Budges vector of this type, or will have a Budges vector in this particular direction, which will be of A by 3 1 1 1. Okay. Suppose we wanted to restore order in this halide, what should be done? Either of this case, if I add a B layer here, okay, the order can be restored, correct? So in a perfect FCC stacking sequence, okay, if a layer is removed, okay, a fault is created, or a layer is added, that same fault can be restored. Okay, that is where already a fault has been created, we have added one layer. But let us not, we will consider the case where in a perfect lattice we add a layer, that we will consider it later. So by removal of a layer or addition of a layer, if the fault can be generated or the fault can be removed, these sort of faults are called as intrinsic stacking faults. Okay. Let us take the case addition of a layer or removal of one layer. Removal of one layer is equivalent to what will be the magnitude of the Budges vector corresponding to that. That vector is going to be A by 3 1 1 1, correct, perpendicular to that direction. For example, in the FCC, you look at this case. Here, from this position, this is the position at which the identical position, this will be the translation vector for the in one direction in FCC lattice, correct? By this translation vector, we are moving from here to an identical position. In between, two more layers are there. Okay. So this vector is there. So if we remove or add one layer, it is equivalent to shortening or increasing it by 1/3 of it, correct? So essentially A by 3 1 1 1 is going to be the fault vector. Okay. So this information that this is the fault vector, this information will be required when we wanted to find out the nature of a stacking fault using transmission electron microscopy. There we should know what is the fault vector. Okay. So what we considered so far was just that a moment of a partial can create a stacking fault. Okay. Can a partial as such be generated in a material, FCC material? No. We considered the case that all perfect dislocations, it does not matter what is the fault energy of the material, perfect dislocations always will have a tendency to split into partials. That is, for example, if we consider this dislocation A by 2, 1 bar 1 0. Okay. This can split into two partials of this type. Okay. Whether this reaction is possible or not, we can just try to find out. This will be A squared by 2, the self energy, the B squared value. Okay. Here it will be A squared by 6, correct? Here it will be another A squared by 6, correct? So if we add them together, then we will find that there is a gain in energy. So inherently this reaction is always results in lowering of the energy of the dislocation. Now the question which arises is that whether this reaction will occur or not, or the reaction has to occur because there is always a lowering of energy. Whether we will be able to observe this reaction or not, this splitting or not. So once such a reaction takes place, okay, in the last class we mentioned that we assume that the dislocation, perfect dislocation has split into a partial of this type. When it has split up into a partial of this type, assume that dislocations are very close to each other. Okay. Now, what is the type of force which will be acting between these dislocations? Okay. That we can try to find out since we know the Budget's vector directions, that we have derived the formula also. Okay. What we will observe is that these dislocations will repel each other. There is a way in which this could be found out. Essentially what is being done is that if we consider the Budget's vector of the two dislocations, okay, this is a thumb rule which is being used. That is, if one dislocation has got a Budget's vector like this, another dislocation has got a Budget's vector like this. Okay. This with respect to a coordinate system which we consider, with respect to origin we can write, one will have a Budget's vector like this, another has got a Budget's vector assuming in this direction. If the angle between these two Budget's vectors is an acute angle, okay, generally the force between these dislocations will be repulsive. Okay. If the angle between them is obtuse angle, then the force is going to be attractive. That means that in this case, like the example which is being shown here, what I had shown is that let us consider with respect to the atom position which is being shown here. From this B position to this B position, a vector A by 2, 1 bar 1 0 will move an atom from this B position to another B position, correct? The same thing can be considered as from this B position, this atom is first moved to a C position, okay, by a partial dislocation having Budget's vector A by 6, 2 bar 1 1, and then another dislocation having a partial Budget's vector A by 6, 1 bar to 1 bar, that comes and moves the atom from this position to this position. That means that this movement has been achieved by moving from here to here and here to here, correct? It's the same. So if you look here, what is the direction of the Burgess vector here in this one? This Burgess vector, if we place with this as the origin, we will find it is in this position. So both angle between them is acute. So these dislocations will repel each other, right? So when these dislocations repel, these dislocations, that is, will try to move apart in this direction. Whenever this dislocation moves apart, since between them they have created a layer which is doesn't have, which has created a fault, okay. So a new surface is being created. So that surface requires some energy to create that surface energy. Suppose we assume that the surface energy is gamma, okay, and we know the separation between the dislocation, what it is going to be per unit length if we consider, into d, the separation between them, that will give the force. This force can be equated to the force which is being acting between the dislocations, okay, correct? We will now come back to this. Essentially, that is what is being done. The force equals G into this expression you remember, which we have derived earlier, GB squared by, and this should be equal to gamma into D. So then we will get an expression for the separation between them. So essentially what is going to happen is that the gain in energy which we have obtained by the dislocation splitting into the partial, okay, that is balanced by the energy which is required to create that surface between, that is essentially a new surface which we are creating by moving the dislocations apart. That surface energy we equate it. Only up to that distance the dislocations will move, okay. What is the consequence of that? Suppose the surface which we are creating has got a very high energy, okay. Then because this formula turns out to be gamma equals G B squared to D, correct, or D equals B squared by gamma. If the gamma is very large, the separation will become very small, correct. Suppose we assume that the gamma is so large that the separation D between them becomes less than the lattice translation vector. Then, though there is an inherent tendency for that splitting to take place will occur, but if they try to move apart, then the surface energy is so high that the separation between them too small to be observed, okay. So essentially if it is within the core radius of the dislocation, then we assume that the dislocations, we are not able to observe it, so we say that the dislocation has not split. We consider it to be remains as a perfect dislocation, correct. That is, after splitting it is such a small value that it's almost one is sitting on top of the other or close to each other, okay. Suppose the stacking fault energy is small, then what will happen is that these dislocations is very small, the separation between them is large, we are able to see these dislocations as two distinct ones, okay. This is what essentially happens in low stacking fault energy material. Then the next case which we have to consider is that suppose the stacking fault energy is of intermediate value, where there is a splitting is there, okay, but the sufficient splitting is going to take place, maybe just about the size of the core of the dislocation, but we are not able to observe experimentally. In such cases, what we will find out is that in most of the experiments, the dislocations will appear to be present in the planar arrangement. Okay. That means that whenever the dislocation sees an obstacle, when the striking fault energy is high, if it is a screw dislocation, it will try to cross slip. Okay. Here, these dislocations will not be able to cross slip. Okay. Okay. For a cross slip, what is the criterion which a dislocation should satisfy? That is, the Burgess vector should lie in two slip planes, correct? So, if we consider a dislocation in 1 plane, which has got a Burgess vector, assume that a by 2, 1 bar 0, okay. This dislocation with the same Burgess vector can lie on 1 bar 1 plane also, correct? If it turns out to be a screw dislocation, the line direction and the Burgess direction is the same, and the line direction is common to both of them. Because of that, a dislocation which is moving in this plane, okay, you assume that dislocation is there in this plane which is moving. As it reaches somewhere here, it sees an obstacle. Since the Burgess vector is in the same direction, a screw dislocation with the same Burgess vector and the line direction can exist in this plane also. So, it will just cross slip onto that plane. That can happen. Okay. That is why, whereas for an edge dislocation, if we consider, the line direction is always 112 type of a direction. Okay, should write it as 112 type of a direction. This is the line direction of for perfect edge dislocation. Okay. And though Burgess vector can be common in two directions, but the line direction cannot be, because of that edge dislocation cannot cross slip. When the dislocation split into partials of this type, this partial, okay, is lying in only this plane. If we consider another 1 plane, a distinct another 112 type of a direction will come for the partials. That means that the Burgess vector of the partial, okay, like in the case of a perfect dislocation, doesn't lie in, does lie only in one particular slip plane. Because of that, the dislocation can never cross slip. Okay. So, what is the consequence of it if the dislocation cannot cross slip? Is that when the dislocation cannot cross slip, okay, that means that the dislocation has to lie in the same slip plane. Okay. Even if the dislocation is split into partials, we are not able to observe them. Since they cannot cross slip, the tendency will be for the dislocation to lie in the same slip plane. That means planar arrangement of dislocations will be seen. That is what it happens in the case of high striking fault energy material. Not high striking, intermediate striking fault energy material. In the case of high striking fault energy material, the cross slip of perfect dislocations will be seen. Intermediate striking fault energy material, we don't see the splitting of the partials, but the tendency for the dislocations to lie in a planar arrangement is being seen. When the striking fault energy is small, the separation between the partials is so large that it is visible very clearly. Okay. Is this clear? Okay. Then another thing also which one should consider it is that if an atom has to move from this B position to this B position, it has to go in a path which is over, because this is a hard sphere model, it is a ball, over which from here to over a curvature of a ball. Okay. Like if this is the surface, from this position to this position, it has to pass over a curvature like this, correct? Like this it has to, like that comes. The other case here, what happens, it's moving from here to another position which is almost the height which it has to overcome is very small and it can come. That means that the tendency to split into partials, okay, this also is an indication that the barrier height is going to be high for going from B to B position, but in FCC if it goes from B to C, because the C has got the same energy but the barrier height is small, so it can go easily. So energetically that is what also we talk about it. So whichever way we look at it, okay, that finally this reaction is always possible, correct? And in this reaction we consider it is that if an atom has to be moved from here to here, the way it has to be moved, first this B atom has to be moved to this position. That is what the first dislocation should do. Okay. So the movement of the first dislocation will move all atoms from B position to C position. When the second dislocation which comes behind, that is if the first dislocation moves, all atoms which are there in this B position here to C position, when the second dislocation which comes trailing behind it, that will move atoms from C position to B position, right? That is how, if we consider between these two dislocations, on either side we will have atoms in the B position, in between atom is going to be there in the C position. Okay. Suppose we consider the reverse reaction, that is, can it go from here to this position and to this position? That means that we have to move from here to a position which is going to be on top of this, which is a barrier, that is from this one it has to come on to this one height. Okay. Generally we will say that it is not possible, okay, but these sort of reactions also do take place, okay, which we will talk about later. This is called as a formation of an extrinsic stacking fault. Okay. Let us confine our attention only to an intrinsic stacking fault for the present. Okay. What will happen to the bottom layer? Bottom layer, the atoms are there in C position, correct? That is, this is A, B, C we have considered. Below A layer, atom will be in that C position. So an atom in the C position can move from here to here and from here to here. So that reaction is possible. That is what essentially we are showing it. Okay. Now what we can make out is that this reaction which we write, here we have to mention from which layer the slip is taking place, above layer or below layer. Okay. That decides what is the type of, which is the one which is the leading dislocation, which is going to be the trailing dislocations. You can see here, right? Here, this is the layer, this dislocation which was initially, which was following, as now is the one which is creating the stacking fault, and the other one is which is whatever the fault which is created when the second dislocation comes, it is just eliminating that fault. Right. The same stacking sequence, because I had shown it in different ways, how one can consider the same stacking fault formation. Like this is ABC type of a stacking sequence, A layer, B layer, different layers are being shown. Here, with respect to this plane, okay, the plane above this C layer, which is the A layer, it is being moved to B layer, okay, by a moment of a dislocation. That dislocation could be, we have considered two types can be there, either 1/3 type, the Frank dislocation, or A/6 111 type. It does not matter what it is, it will move the atoms to this position. this A position to B, the B position is changed to C, because by a moment of a dislocation it will move all the atom layers above that slip plane by the same bias vector. So this is what the stacking sequence now become, right? When that stacking sequences it's completely gone across the surface of the sample, okay, that's full volume of it. This is how it will appear. Both the sides will have a fault which is going to be there, correct? Here the same dislocation reaction which we considered, because in this case which we considered, it is, we have not talked about which is the type of a dislocation reaction which is responsible for fault to be created, but what is the type of stacking sequence, how it is being changed, that is what we have talked about. Now let us look at this case where a moment of a perfect dislocation. Here I had half 1 bar 0 1. Okay, this is the perfect dislocation. This dislocation is split into a partial 1 by 6, 1 bar 2 plus 1 by 6. Okay, this reaction is energetically possible. Okay. Here what I had shown it is the bias vector of these partials are being shown. Okay. Suppose we assume that this dislocation moves from here to this position. Okay. Then if a dislocation moves from here to this position, what should happen? Okay. For the dislocation to reach that position, this atom should be moved from here to this position, correct? All these atoms should be moved from this A position to a B position, has to be shifted. When that is shifted, this would have moved, correct? And then here if you see it, what is it which is going to happen? When this dislocation moves from here to this position, okay, the secondary, because this is the dislocation which is moving in this direction, this dislocation which comes is trying to move in this same direction, because both the dislocations under the application of the force are trying to move in the same direction. Then what essentially it will happen, this will be, when this dislocation reaches here, it is equivalent to this will be replaced from here to this position, A position. This will be replaced to A position. Then when they come to A position, this dislocation line might have shifted and come here, correct? So you can see that this entire layer is now getting shifted from this to another position like this. That is how the dislocation moves. Okay. But the separation between this dislocation is being governed by what is the energy which is required to form the surface when the fault is created, and this energy we call it as the stacking fault energy of the material. Is it clear? So here we have considered an intrinsic stacking fault. Okay. Then what is the separation between the dislocation? That is force balance equation, we can write it. Okay. And from that we can find out what will be the separation. Okay. Here this we have considered it for a perfect screw dislocation. Okay. H dislocation, there will be a 1 by nu will come into this picture. Okay. When we have a screw and an H dislocation, okay, and then this is a sort of that is, if it is a mixed dislocation which is splitting into two partials, okay, then this is how it is going to be the formula for the dislocations which split into partials. Okay. The dislocations which are split into partials also could be a pure screw or a pure edge or a mixed dislocation, right. So, like for perfect dislocation we consider it to be a pure screw or a pure edge or a mixed dislocation. The same is true for partial dislocations also. Okay. So the terms are described here. B1 and B2 are the magnitude of the partials. Theta 1, theta 2 angle between the partials. okay, and their line direction for both the partials, and mu is the shear modulus, okay. D is the separation between the partials, gamma A is the intrinsic stacking fault energy, and nu is the Poisson ratio, okay. This is schematically in most of the books, if you look at it, how this partial separation will be shown, okay. This is how essentially a perfect translation dislocation splits into two partials, and this will be shown like a one dislocation line, okay. Perfect dislocation line, I can take it. This splits it into two partials, and the shaded area is the stacking fault, okay. And suppose we have a, this is the bias vector of this dislocation. If it splits into partial, it will have one bias vector which may be in this direction. There may be another bias vector which may be in this direction. The net product will give this bias vector of the perfect dislocation, okay. That I might not have drawn it correctly, okay. Not correctly in the sense that perfectly, but I hope you understand what I mean, okay. So far what we have considered is essentially a reaction which is intrinsic stacking fault. There is another type of a stacking fault which is there, which we call it as the extrinsic stacking fault, okay. Because the type of reaction which we considered was if a B atom is being shifted from here to this position and then to this position, which is energetically a favorable one. These type of reactions will occur under equilibrium conditions. Suppose we are deforming a material, we are putting an external energy. Then what can happen is that we can try to, since extra energy is being put into deforming the sample, it can move an atom from here to here, or from here to here, or to here to here. All these three are trying to move the atom to a high energy position, correct? Or one more aspect also which one should understand is that once the plane has been decided and we talk with respect to a dislocation moment to create a stacking fault, okay, the movement from here to here easily generates a stacking fault. A movement from here to here is not equivalent because it takes to a position which is not a C position, it takes it to a position which is an A position. This is because this is not a perfect translation vector. A perfect translation vector will shift an atom from one position to an identical position by the moment of that dislocation. Whereas a partial translation vector in one way it moves it to a position which is not equivalent but correspond to another one. But the opposite direction, both of them require different type of energies, correct? So here also we can write a reaction of the type. It can move from here, okay, to here, and then from here to this position if you move it, or from here to here and from here to here. It is essentially equivalent to moving it but requires a very high energy, correct? Let us look at what is the type of a stacking sequence which will be required, okay? Like the way we consider for intrinsic stacking sequence. This is a perfect stacking sequence where no fault is introduced, okay? Suppose I move it, what we have done it is we had moved B by a movement of a partial, okay, to from B position to an A position. So one A atom and another is sitting on A atom. That means this is also a type of a simple cubic lattice which it has generated by moving it from one position to another, or a simple hexagonal lattice it will generate because it moves from all atoms from A to another A position, okay, correct? But suppose I wanted to restore the order in this, what I have to do? I have to add two more layers, then only the order can be restored, correct? That means that the Burgess vector, that means that movement of partials on two layers have to be generated to restore order. That we can consider it here, that we will come back a little bit later. Okay. Another is that in this perfect ordered lattice, okay, if I assume that between B and C, I introduce another layer, A layer. Okay. If I introduce a layer, what happens now? It has become ABC, ABC, AB, AC, AB, AC. This type of a stacking sequence comes. This is the type of stacking sequence which is generated, correct? By adding one layer. To know whether this is equivalent to this, to restore order in this type of a stacking sequence, here again I have to add two layers, but these two layers are added at two different positions. Okay. Here one C layer and adjacent one there, another B layer which is added. So essentially either in this case or in this case, both the cases addition of two layers is required to restore order. Okay. So the fault vector turns out to be different here. Okay. So the same stacking sequence which we talked about with respect to a stacking sequence, we are now looking at it in a different way. That is, the stacking of the different layers are being shown. Okay. With respect to this particular position layer, okay, suppose we move an A atom from here to this position, B position. Okay. Then we create AB, BC, BC, this type of a stacking sequence comes. This is what it generates an intrinsic stacking fault, correct? And if I consider here the stacking sequence, here what I have done it is, instead of moving it from A to B, the next case which we consider is moving from A to C we have done it. That means that these atom C positions are coming on top of each other. So this is a high energy shift. Correct? Okay. Let us look at this high energy shift is being introduced by, suppose this dislocation creates a intrinsic stacking fault. What we have done it is, we have used another dislocation A by C. 112 bar is the dislocation which is in the opposite direction, which has created this atom coming one on top of the other, correct? So after introducing this shift here, okay, suppose in the layer which is just below, we again introduce another stacking fault, because we have seen that on different layers, by moving atoms from one position to another position, we can create a stacking fault. We create an intrinsic stacking fault. By the movement of this atom from C to A position, when we do it, all the atoms above this also will be moved from this B position to a C position. This which has been moved from C, it will now move to A position. This is how they will move, correct? This movement finally leads to a stacking sequence ABC, AB, AC, AB, like that. So in this, if we consider, the stacking sequence become AC, AB type of a stacking sequence. Earlier, the stacking sequence which we considered in intrinsic case is an AB, AB type of a stacking sequence. Here the stacking sequence has become AB, AC type of a stacking sequence. Okay. So, but what we have done, we have generated one stacking fault, a layer above the slip plane, another is layer below the slip plane, another intrinsic type of a stacking fault which has been created. Okay. By doing so, we have generated changed the stacking sequence to AB, AC type of, because AB, AC type of a stacking sequence also in HCP type of a structure. But what one should consider it is that means the two vectors which we have introduced, one vector which has moved from B to C, another vector which has moved from C to A, right, in that below layer. These two Burgess vectors, if we take it, okay, B to C and C to A, and the net sum of it will be equivalent to a moment which gives from A to C type of a stacking moment. Do you understand that? So essentially what we have done it is that we have made shuffling of atoms or movement of atoms on two layers have been implemented by two partials, and the net effect of that with respect to this layer, if we consider it, is moving the atom from A layer to a C layer. Okay. This is how exactly it happens, because the way we can consider it is in this, if we wanted to remove this stacking sequence, we have to add a B layer, right, and another A layer has to be added. Here also if we have to do it, similar thing which has to consider it, that two layers have to be added. Okay. A layer and a B layer has to be added, correct? So if we look at it, both of them are identical, but this high energy fault could be introduced, okay, by making moments on two layers. That is, if we do movement of partials on two layers, that always requires higher energy than making a movement in a single layer. Okay. So this requires a high energy, and because of that, generally the intrinsic stacking faults have got a stacking fault energy which is normally double that of the extrinsic stacking fault has got a energy which is double that of the intrinsic stacking fault energy, roughly 1.5 times to 2 times. That is what essentially it will be. Okay. We will talk about these faults in detail in the next class. Okay. Before that, one more case which we have to consider it is that if we introduce an intrinsic stacking fault successively on every layer, here a B layer is changed to a C layer, okay, that is how this A, C, this, then this A layer is now changed to, okay, another layer, so it goes into a B layer, okay, then this layer is again changed to another layer. Okay. Successively we are introducing stacking faults in each of this layer, then we will see that ABC type of a stacking sequence, here it changes to ABC, then CBA, right. So the stacking sequence reverses. When the stacking sequence is reversed, which is a mirror reflection of each other, then we say it's a twin which has formed. So by introducing intrinsic stacking fault by the same type of a partial Burgess vector on every plane, we can generate a nuclei of a twin. Is it clear? Okay. So considering what we have done so far in this class, we have considered different types of stacking sequences. Okay. We have considered in other way on one-on-one plane. Okay. And we should understand that the peculiarity is that there are two positions are there on every layer which are energetically identical. That is why we are able to generate these faults in a similar type of a situation happens in the case of a close packed plane, okay, that is basal plane. In the case of HCP material also, we generate stacking faults there. Okay, not in all materials we will be generating stacking faults. Okay. So far we have considered the various ways in which the intrinsic and the extrinsic type of stacking fault could be generated. One of the problem which one has to understand here is that the type of reaction which I have written here in this expression, if you look at it, I can put this as the first term and this as the second term, it doesn't make much of a sense. But when you look with respect to the atomic arrangement, that makes a lot of sense to decide which direction, which way the reaction will proceed, correct? So every time one cannot draw a picture of the atomic plane and which direction atom will move, it becomes very difficult. So for this purpose, to overcome this only, a notation which has been used to represent the movement of different dislocations is followed. This is called as a Thomson tetrahedra. That makes the life simpler, and it immediately tells that which will be the leading partial, which will be the trailing partial. These things we can understand. We will talk about this in the later class. We will stop here now. Okay.